Hello and welcome back. In this video, we're going to find the value of these three different definite integrals, and we're not going to be using any calculus on them. Instead, we're going to translate them into area problems and find the corresponding area, and that will give us the value of these definite integrals. So for the first one, it is the integral from 1 to 4 of 5 dx. If you think about what the function f of x or y equals 5 looks like, it's just a horizontal line that has a height of 5. So when we graph this, we can just think again as having a horizontal line, which we'll graph in blue. And we're looking at the area from 1 over to 4. Again, this is not to scale. You'll notice that it's a little wider than it is taller here. But again, we want to find this area. And again, this is 5 on the y-axis. So the idea is just a rectangle, and we can just find the width and the height. So from 1 to 4, we know that's going to be a measurement of 3. And you already know that the height is 5, so the value of this integral is going to just be 3 times 5, or 15. And again, in coming sections, when we do some calculus with this, we're going to actually go through and use integration to find these. Next one up is the integral from 2 to 6 of the function 2x plus 4. Actually, it's from 0 to 6. My apologies. All right, so from 0 to 6, and again, it's 2x plus 4. And again, it's with respect to x. Once again, we will draw a picture. This time around, things are a little different because instead of a horizontal line, we're going to have a line that is actually with an increasing slope. Our intercept we know is going to be at 4. So it's going to start at this point here. And again, we're going all the way over to 6. So 1, 2, 3, 4, 5, and 6. And so we have a line that is going up with a slope of 2. I'm not going to draw it to scale because I'll run out of space. But the idea is that we're going to have this geometric shape to find the area under. And you could interpret this as a trapezoid if you want to, but it's a lot easier in calculus to just interpret this as the sum of two simpler shapes. So instead, what we'll do is just go through and find the area of the rectangle that is the base or bottom of this shape. And then we'll find the area of the triangular portion as well. To do that, we have to kind of mark our points. We know that this point on the y-axis is 4. And we know that if we evaluate the function at 6, that's 2 times 6 plus 4. So that's going to be 12 plus 4, which again, this is not to scale, but the idea is that we are up here at 16. And so we have a width that we know is 6. And then we have this one, which is 4. And then we have the other one, which if we do a little bit of subtraction, we find out is equal to 12 units. So we're going to think of this as the rectangle plus the triangle. So we're going to have, first of all, the rectangular portion, which is 6 by 4, or 6 times 4. And then for the triangular portion, that's 1/2 the base, which we know is going to be 6 units, times the height, which is 12 units. So that's going to be 24 plus 36, which is going to give us a value of 60. So that integral is equal to 60 units of area as an interpretation. For the last one, that is the integral from 0 to 4 of the square root of 16 minus x squared dx. And we may be a little bit rusty with these, but if you look at this, if you take a y equal to the square root of 16 minus x squared, and if you square both sides of this, you actually get y squared is equal to 16 minus x squared, or more importantly, x squared plus y squared equals 16. So the overall shape of this is a circle, but we're looking at the top half of the circle because it's the positive square root, and we're looking at really just a quarter of the circle because we're going from 0 to 4. So the visual to have in mind here is a semicircle that is going to be up at 4 and out at 4. And we just kind of go through and draw the circle. And the value of that integral is the area that is under that circle. And it should be pretty obvious to us that that circle has a radius of 4 units because it's passing through 4 on the x-axis and it is centered at the origin. So our integral is going to be equal to 1/4 of pi times the radius, which is 4 squared. So that's 1/4 of 16, which is actually going to be just 4 times pi. So that integral is actually 4 pi without doing any heavy lifting with calculus. And what's actually going to turn out is you can't even do this integral in Calc 1. It's actually a Calculus 2 problem that you'll see if you take that course in the future. So for these 3 problems here, again, the idea is to look at them from a geometric perspective and think of them as corresponding area problems rather than as integration problems from calculus.